So previously we had a look at forces on charged particles in magnetic fields. Now we're going to have a look at the motion of the charged particle in a magnetic field. A moving charged particle that enters a magnetic field at right angles experiences a force given by the equation F equals qvb. Now this equation usually has a sine theta attached to it, but at 90 degrees at right angles to the field, the sine theta becomes 1, meaning that the maximum force is applied on that particle. Now we can use the right hand palm rule to find the direction of this force. So in the example that we've got here, we've got the magnetic field into the page. The charged particle is a positive particle and it's moving to the right. So with our right hand palm rule, we can see that the force is directed up. Now velocity is a vector quantity and so is force. So when we have a force applied to the particle, it changes the direction of the velocity. So as we move around in small time intervals, the direction of the velocity changes slightly. Now applying our right hand rule to the new direction of velocity, we see that we have a new direction of force. In the diagram that I've got here, you can see the direction of the force is actually always perpendicular to the velocity of the particle, and in our case here, it's pointing towards the center of a circle. Now what we can see here is that the force is perpendicular to the velocity and the speed of the particle doesn't change. That is, the magnitude of the velocity doesn't change. The force on the charged particle remains constant, and what this actually does, it provides an acceleration that changes the direction of the velocity and not its magnitude. We end up getting a circular path of motion, as you can see in the diagram. Now in this particular diagram, we can see that the magnetic field starts in a defined location at point P. So I'll just draw that. Its point P is here. Okay, so the particle enters the field at this location. Now we've got a force that's always acting on the particle the entirety of the time that it's in the field, and you can see it's a constant force and provides a circular motion. So when it gets to point T, the particle leaves the field, and you can see it's in the exact opposite direction as it entered the field. So traveling into the field, the particle is left to right. Traveling out of the field, the particle is right to left, and it is parallel to its initial introduction into the field. As we know a little bit about uniform circular motion from previous topics, we can recognize that this particular moving charge in the magnetic field resembles the uniform circular motion. So we can use some of the formulas that we derived in previous lectures and apply it to this case. So we've got acceleration is equal to v squared on r, and from this we can use Newton's law and find that the force causing this acceleration is given by mv squared on r. But we already know that the force on the charged particle due to the magnetic field is given by the formula F equals qvb. So what we can do, we can equate these two equations and we can rearrange to find the actual radius. So we've got qvb is equal to mv squared on r, and rearranging for the radius, we get the equation down the bottom, which the radius of this uniform circular motion is given by mv on qb. So from the equation, we can see that the radius is dependent on the mass of the particle, the speed of the particle, the charge on the particle, and the strength of the magnetic field that it is moving in. Now in the next couple of slides, I've got some questions to test your knowledge and understanding of concepts from this topic.